Hi and Assalamualaikum everyone. My name is Nur Latifah binti Hasim and today I will explain about displacement of a wave in contrast with distance. Firstly, we will talk about wave. By definition, a wave is a traveling disturbance that transports energy from one place to another. A wave is capable of travel through material faster than the material itself moving. The drawing below show the ocean wave profile and their terms. Okay, first the black straight line represent the still water level or commonly known as a rest position. While the movement of a wave here illustrated by the sinus graph, where the highest point of a wave can reach is known as wave crest, while the lowest point it reach is known as wave trough. A complete oscillation of a wave known as wavelength, while the distance between wave crest and wave trough known as wave height, while half of it known as amplitude. Next, we move to the concept of displacement. Displacements and distance are basically almost the same but slightly different by definition. Displacement can be defined as the measurement of the change of the object from its starting position, while the definition of distance is how far an object traveled. Okay, let's look at the example below. The red arrow is a distance while the yellow arrow is a displacement. Okay, let me explain more detail about the example from the previous. Making the story more interesting, let's say we have Ali and his wife named as Amira. Every morning, Ali will drive to his workplace and at the same time, he will send his wife who is a teacher to school. It took him around 5 kilometers to reach school and continue his travel to the office 3 kilometers. The real distance their home from the office is basically only 4 kilometers. So here we can conclude that the distance that Ali took every morning is around 8 kilometers, which is 5 kilometers to school and plus with 3 kilometers to the office. While the displacement is 4 kilometers. Displacement of a wave. Okay, this picture illustrates a wave which basically I already explained before. So here we have crest, trough, amplitude and equilibrium position. So the displacement can be either positive or negative, and let's assume that the amplitude is 5. So here the red line is illustrate the movement of a wave in sinusoidal form. So here is the starting point of a wave. Okay, let's say a wave is moving and it reached the crest, and here we can say that the displacement is positive, which is 5, where we already mentioned that the amplitude is 5, and then it keep moving and reach the equilibrium point, and here we can say the displacement is 0 because it's on the x-axis and keep moving until it reach a trough, and here we can say that the displacement is negative due to it is below the x-axis and the displacement is -5, and it keep moving until it reach the equilibrium point again, and here we can say that the displacement is 0. Okay, next is harmonic wave displacement. So here we have the equation y x t equal to a sine kx minus omega t. From my readings, I have found that there is two slightly different equation, which is for the positive direction, which is y x t equal to a sine kx minus omega t plus v, while negative direction is y at t equal to a sine kx plus omega t plus phi. Okay, so here is the symbol representation. Okay, so basically in a periodic wave, a pulse travels a distance of one wavelength in a time equal to one period. The speed of the wave can be expressed in terms of these quantities, which is v equal to lambda over t or equal to lambda f. This relationship holds true for any periodic wave. If the individual atoms or molecules in the medium move with simple harmonic motion, the resulting periodic wave has a sinusoidal form. We call it a harmonic wave or a sinusoidal wave. If the displacement of the individual atoms or molecule is perpendicular to the direction the wave is traveling, the wave is called transverse wave. If the displacement is parallel to the direction of travel, the wave is called longitudinal wave or a compression wave. Consider a transverse harmonic wave traveling in the position of positive x direction. Harmonic waves are sinusoidal wave. The displacement y of a particle in the medium is given as a function of x and t by which is the first positive direction, y at t equal to a sine kx minus omega t plus phi. Okay, like I said before here, which is k is the wave number, which is given that k equal to 2 pi over lambda. Next, for angular frequency, which is omega equal to 2 pi over t equal to 2 pi f. And phi is called as phase constant. So referring to this graph, at a fixed time t, the displacement y varies as a function of position x as y equal to a sine kx equal to a sine 2 pi over lambda x. The phase constant phi is determined by the inertial condition of the motion. If at t equal to 0 and x equal to 0, the displacement y is 0. Then phi equal to 0 or pi. If at t equal to 0 and x equal to 0, the displacement has its maximum value, then phi equal to pi over 2. The quantity kx minus omega t plus phi is called the phase. Okay, next referring to the this graph, at fixed position x, the displacement y varies as the function of time as y equal to a sine omega t equal to a sine 2 pi over t with a convenient choice of origin. For the transverse harmonic wave, y at t equal to a sine kx minus omega t plus phi, we may write that as y at t equal to a sine 2 pi over lambda x minus 2 pi ft plus phi equal to a sine 2 pi over lambda times x minus lambda ft plus phi, or using lambda f equal to v and 2 pi over lambda equal to k, which is we can form this positive direction formula. This wave travel into the positive x direction. Let's phi equal to 0. Try to follow some point on the wave. For example, a crest. For a crest, we always have kx minus vt, which is equal to pi over 2. If the time t increase, the position x has to increase to keep that kx minus vt equal to pi over 2. So for the negative direction, it is also the same, almost the same explanation, but it is in a negative direction. So that's all from me. Thank you everyone and have a good day.